Good afternoon, and welcome back to Dr. Logic. Both awkwardly does logic and is really praying that the Zoom whiteboard works on this take of this video. Last time I gave you a definition of what the accessibility relation is in the context of a canonical model, and I promised that I'd tell you something interesting about it. Well, that's the point for this video, if I can get that far. But before we do that, think more generally about what it is that an accessibility relation does just in an ordinary canonical model. This is how we track necessity and possibility. Normally, we think in this very sort of forward-looking way. If I'm at a world W and I want to know, is phi necessary at W, I look ahead to all of the worlds that are accessible from where I am at and I ask, is phi true? But you can also think in a sort of backwards looking way, but and this makes more sense in the context of thinking about possibility. So if I'm a world and phi is true here, well then any world that can see me, phi is going to be possible at that world because you can see me. Phi is true here. That's the kind of relationship that we want to be able to show our definition of accessibility relation captures in the canonical model, not just at the level of truth conditions, but at the level of the structure of the worlds themselves. So the idea is, suppose that we have a maximal consistent set delta that has some formula phi in it, and that we also have that gamma, another maximally consistent set, can see delta. We want it to be the case that possibly phi is in gamma because of this accessibility relation. So that's what it is that I'm going to try to prove to you, assuming I can get the whiteboard to work. Cross fingers. So, new whiteboard. And then we are going to wait, and we're going to wait, and we're going to wait, and we're going to wait, and then hopefully it'll eventually tell me that I can switch to the classic whiteboard, and then we should be fine. So we're going to wait, we're going to wait, and ooh, this isn't looking good, but we'll give it a go anyway. Let's see what we can do with the newfangled whiteboard, which doesn't work well with me. Anyway. Yep, because look at that. I can't even write lemma, and it screws up. Well, let me try one more time. And if it doesn't work, we might just give up. Oh, look at this. Use Whiteboard Classic. I got it. Oh, thank goodness. Again, we will cross our fingers. And it looks like it works. Oh, you guys are in for a treat. So, we've got a lemma that we would like to prove. And it is, so let delta be a maximal S consistent set. Remember, S is just some arbitrary logical system that contains not necessary phi for some formula phi. What we're going to show then is that if we take the box minus of this set and union it with not phi, then this is also going to be S consistent. Now, this doesn't look at all like what I had just previously described to you, but just wait. There's a corollary that will make things make sense. So what we've got our maximal S consistent set delta. It contains a formula of the form not necessarily phi. And then what we're going to do is we'll take the box minus of the set, add not phi to it, and show that the result is going to be another S consistent set. So we're actually going to prove this by contraposition. We're going to show that if this is not consistent, well, then our original set delta was also inconsistent. So that is the order that we're going to go. But I'm going to get a slightly nicer color to do it in. So The proof is by contraposition. And so what we're going to do is we will assume that uh, the box minus of delta, so remember that's all of the formulas in delta that have a box in front of them collected together, all the boxes stripped off. So all of those along with not phi, assume that this is S inconsistent. Then, by definition of inconsistency, we know that there is a finite subset. Let's just say it's gamma 1 all the way up to some gamma n of the box minus of delta, such that in S, we are able to prove that you can't have a conjunction of all of the gammas and not phi. So that's our assumption. So step one. By propositional logic, this is going to be the same thing as saying that if we have the conjunction of all of the gammas, well, then we have to have not phi, or let's just make it easy on ourselves, we have phi. So this is just propositional reasoning that says if you can't have all of these conjuncts together and you've got the first n of them, well, then it's the last one that needs to be the one that's false. From this, we know that I derived rule 1 because this is a rule that holds in any normal modal logic. We can stick boxes on the antecedent and the consequence of this. Then again, by the fact that all of these systems that we are looking at are extensions of K, we can distribute the boxes over the antecedent there so that we've got, if all of the gamma 1 to gamma n are individually necessary, then phi is also going to be necessary. So this is from, oh, it's some theorem that we had a very long time ago, along with the substitution of equivalences. But then we can just use propositional logic to go back to something that we had very similar to the start. Sorry, that should be a parenthesis. Namely, that we have the negation of the conjunction of all of the gammas with boxes on the front and not box phi. Now, we already, oops, again, that needs to be this. So we can prove, again, this is just propositional logic, that we can't have a conjunction of the necessities of all of the gammas and the non-necessity of phi. But this means that delta is inconsistent because, let's look up here, delta is a set that contains not necessarily phi, but where did all of these gamma come from? They're in this box minus of delta, which means that every one of them is in delta with a box on the front of it. So if we assume that the combination of the box minus of delta along with not phi is inconsistent, the only way that can be is if the formula, the maximal consistent set we started with was in fact not consistent. So this is the important bit right here. I then said I would tell you how this actually gets the result that we want. Well, because this is S consistent, remember the Lindenbaum's lemma, every consistent set can be extended to a maximal consistent one. So we have a corollary since the, the box minus of delta with not phi is consistent by Lindenbaum's lemma, it can be extended to a maximally consistent set. And given our definition of what a world is, this is a world in our canonical model. Now, the only other bit that you need to see as to how this gets us the relationship that we want is that not necessarily phi, by things that we proved earlier, is equivalent in logical semantic terms to possibly not phi, but we also know that in one of these maximal consistent sets, not necessarily phi will be a member of the set if and only if possibly not phi is a member of the set. This gets us what we need for our relationship to track the sorts of things that we want it to. And this will all come together in what is one of my favorite lemmas in all of logic, the truth and membership lemma. Okay, first I need to give you the definition of the valuation for the canonical model, but once we've done that, we will have everything that we need to wrap up all of the definitions. Goodness, do we ever do anything other than give definitions and prove things? Welcome to the world of logic. Anyway, we will have to save the next set of definitions and everything till next time. Hopefully the whiteboard will work better then. Until then, take care, enjoy your logic. See you later.